derived our two equations of motion. One that gives theta 1 dot dot, so the angular acceleration of theta 1, and the other one, theta 2 dot dot, which is the angular acceleration of theta 2. And here in LaTeX, I created the two equations, which are exactly identical to that I derived in part 3 of the video of these series of videos, and this is part 4, where we're gonna actually make the code for the double pendulum simulation. And so let's start. First of all, I'm gonna set my my variables. So we have m1. Let's just write the before putting the values in, let's just write the all of the variables we have down. So we have m1, m2, we have l1, we have l2, we have g, we have time, so how long we're gonna formulate our simulation for. We have time duration, which is going to be the number of which is going to be the length of time we're going to use in our Euler approximation. Euler approximation being linking small time intervals for getting a motion that looks like a curvature, a continuous system, but actually it's discrete. But since there's no way to make an actual continuous simulation, we're going to use Euler approximation, and for that we're going to need our duration of time. So the small length of time that we're going to use in our Euler approximation. We're going to set time iteration, which is going to be the number of iterations of the time duration in t. We're going to have our angular quantities. So we're going to have the theta 1 itself, and because we don't have theta here, we're going to use angle 1. We're going to have the velocity of angle 1. We're going to have the acceleration of angle 1. And the same thing for angle 2. The velocity of angle 2, acceleration of angle 2. Alright, and we're going to have to set our first values. So we're going to need a starting point. So again, we're going to need a starting point for angle 1, a starting point for angle 1's velocity, a starting point for angle 1's acceleration, a starting point for angle 2, the same. Angle 2 velocity, angle 2 acceleration. And yeah, that's going to be all the variables we are going to need. So now I'm going to set the values for these variables. So these, from this to here, these are all going to be constants. So I'm just going to set this as like 5. L1 is going to be maybe 30. L2 going to be, maybe let's use something shorter, so maybe 22. For G, we're going to set 9.81, of course. For time, we're going to run this simulation for 100 seconds. And our time duration would be equal to something short, so 0.01 would be reasonable, I guess. For time iteration, we're going to use t divided by time duration, because that's the number of time durations there is in the number of iterations there are for the time duration and the time. For angle 1, we're going to set it as a vector with first initial values of 0. So we're going to fill it with zeros, t iteration amounts of 0, and this indicates the column, this indicates the row, this indicates the columns. It's going to be a horizontal vector. We're going to do the same thing for this here. So we're going to fill it with t iteration number of zeros and a column vector. Same for here. And the same for here. And now for our initial value, I'm going to use something like, maybe a reasonable value would be, so from the normal, I'm going to use 135 degrees, which is going to be 3 pi divided by 4. So 3 pi divided by 4, that's 135 degrees from the normal. And this is going to be 45 degrees from the normal if we set the normal as the top, or if I set the normal as the downwards arrow, so something that looks like that, we're going to have 135 degrees from the normal. And the same for the initial conditions of angle 2. So 3 times pi divided by 4. And for the velocity and acceleration, we're going to set all of them as 0 and see what effect the only gravity would have on the system. So these velocity and acceleration, they're all set as 0, and the angular positions are set as 135 degrees from the bottom normal line. Now let's set our video. So we have to set video right there. And our name of the video would be Double Pendulum Movie. Double Pendulum Movie .avi. And our frame rate is going to be 60. That's reasonable. And so now let's open our video. Alright. So we're going to run this code for the number of t iterations we have. So from 1 to t iteration. We're going to have, so in Euler approximation, we said as, so the angular position of the n plus 1's variable is going to be the angular position of the nth variable plus the angular velocity of the nth variable times the length of the time duration. This is basically what we do in the Euler approximation. And we do the same thing for angular velocity. So the angular velocity of the n plus 1's is going to be the angular velocity of the n's plus the angular acceleration of the n's times the time duration. And we do the same thing for, first of all, let's do the same thing for angle 2, so angle 2 n plus 1. I'm just going to copy all that, and so the code is exactly the same. So we get angle 2, equal to angle 2 here, plus angle 2 here, plus angle 2 here, and plus angle 2 here, and plus angle 2 here. Angle 2, angle 2, angle 2, angle 2, angle 2, angle 2. Right, now we have to set our angular acceleration of the n plus 1's. But now we have a problem. If we, as I said before in part 2 or 3, I guess, if we go down with this Euler's approximation, we don't stop. And so we need to set something. And that something here is going to be our angular acceleration, which we define over here. So now, to make the process simpler, I'm going to divide. This is so this here is such a long fraction. This has a lot of terms and 2 terms in the denominator, a lot of terms in the numerator. And so I'm going to divide my code by some parts. So I'm going to set my numerator 1. So my first term in the numerator here, my second term in the numerator, my third term in the numerator, my fourth term in the numerator. So I'm going to have num 1 to num 4, num 2, num 3, and num 4. And for the denominator, I'm going to have denominator 1 and denominator 2. Because the denominator here has 1 and 2 terms. Alright, so let's look at numerator 1. Numerator 1 is going to be equal to m2 times g, so look here, look over here, m2 times g times the sine of a2 times the cosine of a1 minus a2. That's the first term. And now we have, you gotta realize that for each of the n2s and 1s and a minus 2s, we're gonna have to get the n plus 1s value. Because at the end, when we're gonna define a1 of the a1 under bar a, which is the angular acceleration of a1, we're gonna set that as a1. We're gonna define that as the n plus 1s term. So every angular quantity here must have an n plus 1. So I'm gonna do that after I define all each numerator value. So n plus 1 here, n plus 1 here. Now let's look at numerator 2. Numerator 2 would be minus m2 times, so it's going to be our second term here, times something of squared, and that something would be our the angular velocity of angle 2. So a2 under bar v to the square. And we're going to need another bracket, like that. It's that squared times L2, so L2, times sine of A1 minus A2. Now again, we need A plus 1, so A2 velocity of n plus 1, we need A1 of n plus 1, and for the same, n2 of n plus 1. Now let's look at the third term in the numerator. That's also a minus value, so we have is equal to minus n2 times, again, something squared, and that something is going to be our angular velocity of angle 1. So angle 1 of velocity squared, and that's times L1 times sine of A1 minus A2, and times cosine of A1 minus A2. So we have sine A1 minus A2 times cosine of A1 minus A2. Now again, we have all the angular quantities, so we get n plus 1s. Here also n plus 1s. Here also n plus 1s. Now this is a tedious process, but it is necessary, so don't forget to do this. Because at the end, I said before, we're defining the n plus 1s term of A1 acceleration, the angular acceleration of A1. We're going to have to define everything in terms of the n plus 1s term of the angular quantities. Let's get num 4. Num 4 is going to be equal to minus m1 plus m2 times g times sine of theta 1. That was good. So we have angular 1. G times sine A1, and we have A1, again, the n plus 1 term of A1. So we defined all our numerators. Now let's go down to our denominator. We have the first term in our denominator as equal to m1 plus m2 times L1. That's pretty straightforward. And the second term in the denominator is going to be minus m2 times L1. Now cosine of that squared. So we're going to have times something squared. It's always easy to think of it as brackets because of make the brackets first, because by the end of the expression you're going to have too many brackets that it's going to jumble up your mind. So we have something squared, and that something is cosine of A1 minus A2. So we have cosine of A1 minus A2 entirely squared. And again, we have the angular quantity, so we have n plus 1's term, and for A2 again, n plus 1's term. Alright, there's no errors up until now, so let's save it. Yeah, no errors. That's a good sign. And now, we're now going to have to define finally our angular acceleration of the n plus 1's term. And we said that's equal to our we already defined our fraction in terms of numerators and denominators, so we only have to do is the only thing we have to do is something divided by something, and that first the something here, so that's the numerator, that's the sum of all my numerator terms, so m1 and 2, num3 plus num4, and then the denominator is going to be denominator 1 plus denominator 2. Alright, that's done. Now let's look at A2. Let's do the same thing for A2. Let's have it spaced out. Alright, we have for A2, again, we have to define its acceleration, the n+1's term of its acceleration. And now again, we look at this here, and we see that there are 3 terms in the numerator and only 1 term in the denominator. And so we set numerator 1, numerator 2, and sorry, I can't use the same one, so I'm going to set numerator, let's say numerator underbar 1, numerator underbar 2, numerator underbar 3, and denominator is just L2, so I don't really have to do that. And so for numerator 1, we have this over here. So something squared, and then something is the angular velocity of A1, the velocity of A1 like that, and then times L1, and just in case, I'm going to add a bracket here. I don't think it's necessary, but just in case. And we have sine of A1 minus A2. Now for here, as I did before, we need the n+1's term. And again at here, we need the n+1's term. And here too. Velocity of n+1's term squared. Now for the second term, we have a negative value, so we have this is interesting. So we are using this value here, the value that we defined here as A1 underbar A. We're going to use it again here, but there's no problem in doing this because we already defined our angular acceleration of angle 1. So we have angle 1 minus angle 1 acceleration times L1 times L1 times cosine of angle 1 minus angle 2. That's it. And again here we need the n+1's term for every angular quantity, so A1 again of n+1's term, and A2 again of n+1's term. And now let's look at our final term in the numerator. That's really easy. It's just going to be minus g times sine of angle 2. And again, we need the n+1's term. Alright, so now, finally, our A2, the angular acceleration of our n2 would be something divided by, we have L2 in the bottom, so something divided by L2, and that something is going to be our sum of the numerators, so numerator 1, numerator 2, numerator 3. And now that's it. We have our angular acceleration of 1, angular acceleration of angle 2. And so now all we have to do is set up our pendulum system, like our diagram, as you call it. And so we're going to have the, I'd say, the x quantity, so the x coordinate of 1, so I'm going to set that as px1. And that's going to be equal to L1 times sine of A1. And again, we now need the nth term, because this is a general term, not the n+1's term. This has nothing to do with the Euler approximation. We're just going to plot every point on that nth iteration. So px1 is going to be that. Py1 is the y coordinate of the first mass, the first blob, I should say, and that's going to be minus L1 and cosine of A1, and the nth term. And if you're not getting why I do this, then you could go and look at the diagram I drew on part 1 or part 3, and you see why I'm setting these values as this. Now for px2, we're going to get px1 extended, so px1 plus L2 times sine of A2, and again we have the nth term of M2. And for py2, we're going to have py1 minus L2 times cosine of A2, and again we're going to have the nth term. Alright, so now what we're going to do is create a pen and set our limit. So that this limit is going to be where our video would be defined as. So like, because our pendulum system, it can't like go out of our axis, like go out of our video, like into the walls. So this is basically setting our walls. Limit would be L1 plus L2. That's going to be the limit for what we're going to do. And so now what I'm going to do is fill our canvas. That's going to be, this is quite a very tedious process. So a rectangle, so this rectangle will be x coordinate, y coordinate, and get minus limit minus about 0.2 would be appropriate, times limit, and limit plus 0.2 times limit, and plus 0.2 times limit, limit plus 0.2, and minus limit, minus 0.2 times limit. So minus here, minus plus minus. That is gonna be right, yeah. And so for this here, we're gonna do the same thing. And we're going to set the color of our canvas as white, so get a W. And now I'm going to plot my blob first. No, I'm going to plot our line first. So the pendulum string, that's going to be. I'm going to set our pendulum string first, and that's going to be x coordinate, y coordinate, red, and our line width is going to be 2. And that's the x coordinate of our line would be from 0 to px1, and for y it's going to be from 0 to py1. Because it's a string, we're going to link 2 coordinates, and the first coordinate would be 0 times. It's going to be here and then here. Imagine like the x coordinate to so like 0,0 to px1 times py1 that's going to be represented as something like that. And we're going to now set our blob, so that's going to be very similar. We're going to put the coordinate of our blob would be px1 times py1, and we're going to use a marker that does that. Marker size as about 10. Marker face color would be red. So our first blob are both going to be red, so the string and the blob is going to be red. And our marker edge color is also going to be red. Alright. And now we do the same thing for our second blob. But now our second blob is going to be from px1 times py1 to px2 times py2. And also it's going to be not red, it's going to be blue, line with same. Again here, now the new coordinate is going to be px2 times py2. And all of them are going to be blue. Oh no, this is going to be blue. This here is also going to be blue. Alright, now if we set our limits, so this is going to be again our limits. That's going to be minus limit, minus 0.2 times limit, limit plus 0.2 times limit, y limit, very similar. We have minus limit, minus 0.2 times limit, limit plus 0.2 times limit. Right, that looks good for me. Is there any mistake I made? Because I made quite a lot of mistakes, I've got to check all these. I think I'm doing well so far. Okay, let's move on. Now we're basically done. We set our title as double pendulum simulation. And then set our video. And that's it. That's basically it. Now we have successfully made our code. Is this going to work? I'm quite confident. So let's see. If we save it and run it, we're going to see that our canvas is going to hopefully going to appear here, somewhere here. It's here. Oh, yeah. So yeah, our figure appeared here. And as you can see, it's really, really slow because I set my time duration here is 0.01. But if you wait with quite a bit of patience, you're going to see that the coordinates hopefully are changing. So slowly but surely they are moving. Are they? Is there an error? It says there's an error. Seems like it's not moving, so let's see what the problem is. But so we have oh, this. And so let's look at our figure now. Hopefully it's working now. There's no errors this time. So x coordinate was like that. Is something happening? Let's run it again. So slowly but surely it has to be moving. Is it not? Is there something wrong? Alright, so after I do my debugging, I think somewhere there's a problem in the code, and I'll come back after I finish debugging. So let's see there. After after the figure pop-up appears, I can't. If I touch it, it doesn't work because the video gets cut off. So let's do that. Let's not touch it. So I'm gonna run it. The figure appears here, and now you can see that slowly but surely they are moving. So you can see that they're tingling like that. See the little tingle? The shape has clearly deformed. As you can see, yeah, now it's better. You see, as they're accelerating due to gravity, their shape is being distorted, and you can see that although now, like as of now, you can't see whether the double pendulum simulation works or not. So far, I think it is working. There's no change to the code; it's as it is. And also, I'm gonna upload the code onto the description below, and in the description below. So if you wanna do the same thing in MATLAB, you could use this code. I'm gonna share it to you in the comment in the descriptions below. And yeah, so what I'm gonna do is I'm gonna let this go for quite a while, and if it finishes, then I'm gonna download the video file and show that video file and this part of the video, and which was the final part of our video. And so thank you for watching. Yeah, I'm gonna say goodbye in the quite a few while later after I download the video file. And so yeah, see you after after this simulation hopefully finishes, which is gonna take quite a long time, but I hope it does. So bye bye. Still, yeah, it's moving. So the double pendulum, so like the 100 seconds that I said has not yet finished. It has to be like about 2 hours, 1 hour and a half since I recorded the last part, but it's still moving. So for now, I'm just gonna cut this. So I'm gonna close it, and then I'm gonna find this file on Finder. So go to here, show in Finder. Okay. Yeah, and you can see that it's here, and it's 87.4 megabytes, and it's an AVI file, which means that I can't open it with my computer over here. So after it finishes downloading, I'm gonna open it with as an MP4 file. So I'm gonna search AVI to MP4. Go to this site. I'm gonna select my file, so I know that my file is in the MATLAB folder of documents. So MATLAB, over here. I'm gonna open this, and I'm gonna press convert to MP4, which I know that the computer can open. And so after this finishes, and so if I press resume, you could see that at first it's really slow, but as it goes down, it accelerates, and it performs double pendulum motion. And so I guess it is a succeed. I succeeded in creating a double pendulum simulation. As you can see, and it goes to the top. In general, they slow down, but the bottom one swings. And although you can of course see it, if I draw a graph that indicates kinetic energy and potential energy, you would be able to see that they're conserved. And of course, because we're using Euler Approximation, it won't be perfectly conserved as it would in the real world. But yeah, if I get a chance, then I would also I also draw the energy graphs of both indicating both kinetic energy and mechanical energy. If I do have a chance to do that, I will do that. And so thank you very much. That was the final part of creating a double pendulum simulation with MATLAB done. I hope you liked it. Please press like and subscribe. And yeah, that was Joe's Physics Corner, creating a double pendulum simulation. I guess, would this be part 4? Yeah, part 4 done. Thank you all, and see you later. Bye bye. And of course, at the end of the video, I'll upload the full version of this simulation. So, goodbye. And this is the video file, fast forwarded in 4 times the speed of the original.